All right. So welcome back to another Math 230, 231 GSG session. Before we get started, I'm going to start off with a announcement from Penn State Learning. So if you guys are in State College over summer, Penn State Learning tutoring services are starting next Monday, June 10th. And so we'll have tutoring services from 12 till 5 p.m. every weekday at Buki 228. And we'll do every math course up till Math 251. Okay. So if you have any questions, just feel free to stop by. All right, so getting to today's session, we'll be covering chapters 14.1 till 14.4. And so, yeah, we'll be continuing with practice problems for that. So for 14.1, it was the introduction to, let me see. All right, so 14.1 was the introduction to functions of several variables, right? So functions of several variables. So in lecture and in recitation yesterday, you guys were introduced to domains, ranges of these functions. In today's session, I'll be focusing more to the level curves. So I'll be focusing on the level curves of these functions. And the second thing I'll be focusing on today's session will be contour maps. Okay, so we'll look at examples of those today. All right, so let me start off with level curves. Let's look at an example from the textbook. All right, so first question will actually be 14.1, number 33. Okay, so I actually have a picture of that on my screen. Let me just share that real quick. All right, so show you screen, sure. All right, so yeah. All right, so a contour map for a function f is shown. Use it to estimate the values of f, -3, 3, and f3, -2. And what can you say about the shape of the graph? All right, so let me start off with contour maps. All right, so just like how archaeologists use contour maps to kind of like survey an excavation site, that's how I think of it. So these lines with the numerical numbers representing like 70 for this curve right here, right? 70, 60 for this curve right there, 50 for this curve right there, and 40 for this curve. Imagine that as kind of like the z value for this surface. So if I were to, so this contour map is a function for f, right? And so in order to find f -3, 3, we just look at the x value when it's at 3. So 0, 1, 2, 3, or -3, sorry, 0, 1, 2, -3, and a positive y value of 3. So 1, 2, 3. So that would be that point right there. All right. So this will actually map up to a z value in between 50 and 60, right? Remember, these contour lines, right? These lines just basically represent kind of like the height or like the z value of that surface. Okay, so yeah, this will roughly be between 50 and 60. We can say roughly 55. All right, and for f of 3, -2, that's the same thing as 1, 2, 3, and then a y value of -2, which is that spot right there. So in between 30 and 40. Okay, so we have a z value in between 40, or yeah, between 30 and 40. Right, and yeah, we can just estimate that as, let's say, 35. Okay, now more importantly, what can we say about the shape of this graph? So what I look at is usually the distance between these curves. So as you can see, when you're approaching a greater value of y, you see that these curves expand a lot farther, like the gaps are farther. So this gap right here, in comparison to that gap right here, we can say that it's pretty far compared to these gaps underneath the x-axis, right? So what we can say is that in the z-axis, the slope or this side of the graph is a lot steeper than this side of the graph or the surface. Okay, and this will be helpful in actually representing. So the next few questions will be actually drawing out the function using a contour map. Okay, this would be really useful. This concept would be really useful to use. All right, so any questions so far regarding like the basic idea of contour maps? All right, perfect. All right, so let's go to questions regarding mapping out the actual function from a contour map. All right, so this will be number 41 from 14.1. Okay, and again, I have a picture of this. All right, so let's look at this. A contour map of function is shown. Let's start with number 41. Okay. So for number 41, what we can see is that, why can't I use, oh, there you go. All right, so what we can see is that the z values or these curves are sloping upwards starting from the origin, or like the surfaces are going incrementally up. So 11, 12, 13, 14. So for 41, if I were to map this out, let me start off by drawing the axis, x, y. And let's say z is up here, right hand rule. And then let's just assume that the middle of the curve has a surface level of 0 and it goes up till 14. How we can draw this is that at level 0 we have a small initial circle, right? A small circle at 0. What happens is as the circles get bigger, the surface or the z value of this contour map gets higher. And so, yes, I hope this drawing is clear enough. We're going to get something like this as the function of f based off that contour map, right? Because as the circles get bigger, as the radius of each circle gets bigger, its surface level also increments upwards. So that's like this 14 right here. I basically signify that as the same thing as your z value, or like the height of the contour map. Okay. So that's 41. It's going to look something like this. All right, so let's look at 42 now. Yeah, this should also be in the homework. So you guys should have plenty of practice for this. Let's clear this out. All right, so for 42, again, same thing. What we could say is that, let's start off by drawing an axis. 42, so we have x, we have y, and we have z. All right, okay. So as it goes further along the y-axis or in the positive direction, we see that the curves or the levels, surface levels, get smaller, or like it goes to a negative z value. All right, so I'm just gonna say that we have initially a height or a z value of 8 with this curve right here, and that's gonna represent something like this right there, right? Looks like a parabola, and then it decrements down, or it basically steps down steeply for the first few curves. So just gonna draw like that. Something. Oh, yeah, this drawing. Let me just restart this drawing. So let's see if we can draw this nicely. So we have that right there. Then increments down and it approaches more towards the origin, like the x and the y when 0. So it goes towards the origin and it goes below, it goes to a negative value of z. So we're trying to make these curves as close as I can. Yeah, excuse my drawings. And then I go further down and further down. So the graph is going to look something like that, where it basically slopes downwards as it goes farther into the positive direction of y. Okay. And that's based off basically the level of each curve. All right, that's 42. Now let's go with one more, 43. Yeah, let's start at, 43, be a good example. All right, so let's look at 43. All right, so 43, we have a surface level 0 right there. So 0, 0, 0. So if I have to draw this out, I can start off by just drawing these zeros out. All right, so if I have to draw out x, y, and z up here, I see that there is a linear curve diagonal across x, y, and then these are also at a surface level of 0. My z value for these curves are at 0. All right, so what happens as it approaches a positive value of y, or like what happens on this side of the graph? It basically increments upwards, right? Because it goes from 1, 2, 3, 4, 5. So it basically goes up. So if I can draw that out, it's gonna look something like a parabola again. And it increments up the farther it goes away from the origin. It's going to look something like this. All right. And then same thing for the other side. So 1, 2, 3, 4, 5. It's going to look something like this. It's basically going to mimic this side of the graph. So sort of, erase this. Upwards and up. Again, excuse the drawing, but it's going to look something like that, where it goes basically, the graph should increment upwards. So something like that. And you see this diagonal line should be at 0. So it should slope downwards and should go down to 0 at this. Okay. All right. Okay. From the textbook, it says just make a rough sketch. But for the web design homework, you guys will get options for which function it will mimic. And again, just go back to the definition of a contour map. Just what I normally do is, as you saw, just analyze how it is acting in the z direction, right? If it increments up or downwards. All right, and let's actually do the last one, 44. Okay, so you can see that it's basically squares starting from the origin at a high point of z is equal to 3, and then decrements down to -3. So let's try that out. X, Y, and Z. All right. So at 3, we have a square, a small square. All right. A small square at 3. Let's say Z is equal to 3. And then, it's going to be a point at 3. All right. It's going to be a point at 3. Now that first square is going to be a 2. So that's going to represent that square. And then square gets bigger and it basically goes downwards. So, and these curves get basically as smaller z value. So it's going to look something like that. It's going to look something like a pyramid, like square pyramid. Okay. And then it just goes down all the way down till -3. Okay, at z is going to have 3. So that's going to be what this surface looks like. Okay, so that's number 44. All right, so any questions regarding contour maps and correlating that to sketches of the graph of f? All right, perfect. All right, so that's pretty much 14.1. Everything else I think from 14.1 is either covered in lecture or recitation. Right, and I think recitation yesterday covered a lot about sketching graphs of functions. All right, so I'll move on to 14.2, limits. I think this is one of the bigger topics in chapter 14. So let me start off by starting a new whiteboard. All right. So for chapter 14.2, right, I think of limits basically as, so in R3, I think of it as a function, or rather different paths going to a certain point, and you have to make sure that all these paths, so if a limit exists, we have different paths approaching the same exact point. While if a limit doesn't exist, we have basically some paths which don't correlate to like a certain specific point. This will probably be more clear once we start looking at questions. All right. So normally, okay, let me start off with how I approach these limit questions. So for step 1, what I normally do is I look at the equation of the function given to me. So let me start off with, let me give you a function real quick. So 14.2, number 9. All right, so I'll keep this whiteboard up here and I'll start a new one. All right, so I'm looking at question number 9 from 14.2. So it says basically you're trying to find the limit as x comma y approaches 0, 0 of the function x4 minus 4y squared all over x squared plus 2y squared. All right. So I'm looking generally for something weird that can happen. So like looking at this question right here, since the parent function is a rational function, this function is going to be continuous except for when the denominator equals to 0, right? So things like that. All right, so basically, yeah, those cases where you're dividing by like a 0, so like those weird cases that can come up, So example of this, as I mentioned, is dividing by 0. And then also looking at whether the function is continuous or completely continuous. The function given is continuous, right? Since if we're given a continuous function, we basically can compute, or we can basically say that the limit exists for a certain function. All right, so now going back to this, what I tend to do next is I look at the limit along, the x-axis and the y-axis at the specified point. So just going back to this, the second thing I look at is I check limits at specified point along the x and y-axis. So what I mean by that is I look at this question right here, and I basically, when you're looking at the x-axis, that's basically when y is equal to 0, right? So if this was f of x right here, or f of x comma y, rather, comma y, I basically try and find f of x. In case is going to be the same thing as x to the power of 4 all over x squared, right? So this implies that this is x squared. Okay, And based off this, if you take the limit, you would basically verify that as f of x approaches the specified point at 0, 0, this limit is going to approach 0. Right? Remember, at point 0, comma 0. Because if plugging 0 there, we get a 0, right? So this is also key at point 0. So we just use red to highlight this. And again, this is along, oh, sorry. Yeah, let me just red for that. Along the x-axis, because I'm basically setting y equals 0. So I normally check that out first. And the second thing I also do is I check the x-axis, and now I'm gonna check the y-axis. Okay, so if x is equal to 0, I have f0 comma y, which is the same thing as negative 4y squared all over 2y squared. But what do you notice here? We end up with a negative 2. So this implies that as f of x, y approaches 0, 0, we have the limit approaching a negative 2. And since these two limits are not equal to each other, right, we can say that the limit based off this, we can say, let me use red. We can say that limit does not exist. Okay. All right. This is just basically looking at two different paths, one along the x-axis and one along the y-axis. Right. So that's how I usually start the question. So this is a great example for number 9. All right. And now let's look at another example. So let's say we have, I'm going to pick out number 11 from 14.3. All right, so for number 11, we have the limit of x comma y approaching 0 comma 0 of y squared sine squared x, and that is all over x to the power 4 plus y to the power 4. Okay. So we have a limit. So again, first thing, going back to that page from the whiteboard, if I can go back, look at weird cases that can come up. So clearly, this is not completely continuous. So I have to watch out when the denominator is equal to 0, like in this case. Or if I plug in 0 and 0, I get basically 0 over 0. All right, so that doesn't work out. Now, the second thing I do is I check the limits along each axis. So check if x is equal to 0, I get, what do I get? So I get y squared all over y fourth, right? Which is the same thing as 1 over y squared. Okay, so wait, let me just check that. No, actually, that's not right. Sorry, that's my bad. So if x is actually equal to 0, we get y squared times 0 all over 0 plus y to the 4th. And that's going to be 0, right? So if x is equal to 0, we get 0. So this implies that the limit, or rather f of x approaches, there's a limit as x approaches, or x comma y, approaches 0, 0 of fx comma y. That's going to be 0 along the y-axis. All right. Now, if y is equal to 0, we should get the same thing, because it'll be 0 times sine squared x all over x power 4 plus 0. That's also going to be 0. So f of x comma y also approaches 0 along the x-axis. Right? X-axis. But again, as mentioned in recitation yesterday, this doesn't cover all the different paths going to the origin, right? Because our specified point is the origin. This doesn't specify all the points. So what Dr. Roberts covered yesterday is what we should do next. And that's why I'm gonna go back to that. whiteboard. And the third thing I do is I usually also check different lines. Different lines. Okay. This basically also represents other paths that you can basically go to the origin or like the specified point of the limit. And that I'm going to just specify as y is equal to mx, right? Because this signifies basically all the different lines just with a certain slope. All right, so going back to this equation right here, let's set, okay, let me just pull another whiteboard. Let's set y is equal to mx. So going back to fx comma mx, that's going to be the same thing as x squared or mx squared sine squared x all over x to the power 4 plus m to the power of 4 or mx to the power of 4. Right, so if I simplify this down, I can mx squared sine squared x all over, let's see, x to the power 4, 1 plus m to the power 4, right? We can simplify this further into m sine squared x all over x squared times 1 plus m4, right? So just using that substitution of the different lines. Okay, so what's next is we can say that we're trying to find the limit as x approaches 0 for this function right here, right, of m sine squared x all over x squared times 1 plus m squared. Okay, so what we want is we want a function which doesn't depend on m. So like it has to always like converge to a certain point. That makes sense? Okay, so for this question right here, we have, so we don't want any m's. If there are m's, or like if it's only dictated by m's, then that implies that the limit only, like the limit is entirely dependent on m. So what I can do further for this is I can just isolate the m's by itself. And the reason why I want to do that is because this limit should look kind of familiar to you guys, right? Because if I can rewrite this as m divided by 1 plus m squared, and this as sine x over x squared, we can say the limit of x approaching 0 of sine x over x is the same thing as 1, right? So we can further simplify this into m over 1 plus m squared. All right. And in this case, since this limit of this function depends on an m, or rather like this limit right here depends on the m, my limit does not exist. For a given function. So in this case, where I have, for number 11, where I have y squared sine squared x all over x power 4 plus y 4, this limit does not exist, because it solely depends on m. Okay. Any questions off of that? Perfect. Okay, so let's go on to the next question. All right, so that was number 11, and let's go to number 13, right? So for number 13. So we have the limit as x comma y approaches 0, 0, and xy all over square root of x squared plus y squared. So for this case, again, I want to do the same procedure. So I check along the y-axis. So that's going to be 0, right? Approaches 0 along y-axis. And it should, yes, it is the same thing along the x-axis. All right, so that was step number 2 done. Again, this is a rational function, so I can't have a 0 underneath. All right, now the second thing I want to do again is from the steps before is I want to set y is equal to mx plus mx. Right, so if you look at fx comma mx, we get that x times mx all over square root of x squared plus mx squared, right? And that's going to simplify down to mx squared all over the square root of x squared times 1 plus m squared. And that's going to equal mx squared all over x times square root of 1 plus m squared, which is equal to mx over square root of 1 plus m squared. And so if I were to take this limit, it'll be the limit as x approaches 0 of f of x comma mx. And based off that, if you plug in a 0 right there, you would always get a value of 0. So this limit does approach to a certain point, or to 0 rather. It might be a possibility that it does approach that limit of 0, right? And you can see, compared to the previous question, that this limit is dependent on m. This limit right here, based off this procedure, does not depend on m. Because if x were to be 0, this would automatically be solved to 0. Or yeah, this would compute to 0. Yeah. But it doesn't end there. The last thing I do to check whether these questions or whether a limit exists is that I also check for different paths, or like other paths that can possibly go towards the point. So in this case, we check along the x-axis, we check along the y-axis, and we check different lines. But there are other different paths that can go to a specified point. And what was covered during recitation yesterday was that you guys would cover, so Dr. Roberts covered that, or went with a polynomial, so y equals x squared. Okay, so we should also check whether that works for the specified function. So for this, I'll do the same thing. Instead of y is equal to mx, I'm going to set that y is equal to x squared. And then I'll basically take the limit of x approaching 0 of, so in this case, instead of mx, I get x squared. So that would be x times x squared all over the square root of x squared plus x power 4. And then that's going to be the limit as x approaches 0 of x cubed all over the square root of x squared times 1 plus x squared. That'll be the limit as x approaches 0 of x squared divided by square root of 1 plus x squared. And that actually does compute to 0, right? That'll be 0 over 1, which is the same thing as 0. Okay. Yeah. All right. And yeah, that's basically it for number 13. So the last thing you want to do is step number 4 is check other paths. So like an example is plugging in a polynomial instead of a line or linear curve. All right, and that's number 13 and number 17. Okay. Let's go with one more or two more questions. All right, so for number 17, I have that the limit as x comma y approaches 0, or the origin and x squared plus y squared all over the square root of x squared plus y squared plus 1 minus 1 outside the radical. All right, so another thing mentioned also in lecture is that whenever you're dealing with these kind of questions, you can also apply algebraic tricks. So again, I'll go through the same procedure. So I'll check along the x-axis, so y equals 0. I get x squared all over the square root of x squared plus 1, 1 minus 1. Okay, let's see it that. X squared over square root of x squared plus 1. Can we simplify that? Right, you kind of stuck 0 square root 1. Yeah, this wouldn't help you in this case. So what I would do in this question is I would actually just simplify this question first. So instead of checking paths, what I can do is I can apply algebra tricks, right? Because whenever I'm dealing with radical, I want to get rid of this. So I can multiply by its conjugate in the denominator. So I can multiply this by square root of x squared plus y squared plus 1. And let's see if that helps out the question. Okay. I'm thinking, yeah, this should help it out. Let's see. So we have the limit as x comma y approaches 0 comma 0. Then the numerator is going to be 1x squared plus y squared multiplied by the square root of x squared plus y squared plus 1. All right, so that's, and then plus 1 outside. For the denominator, this is going to multiply out to x squared, or I want to get rid of, yeah, basically multiplying by its conjugate. So I get rid of this radical in the bottom, x squared plus y squared plus 1. And multiplying that by that by that would cancel out, and I would have a -1 outside. All right. So again, this simplifies down to the limit as x comma y approaches 0 comma 0 of x squared plus y squared multiplied by the square root of x squared plus y squared plus 1 all over the x squared plus y squared. And you see how that helps is that we can actually cancel these two factors out. Okay. Yeah, stop me whenever you have any questions. So yeah, feel free to stop me anytime. So these two factors cancel out, and we're left with a limit as x comma y approaches 0 comma 0 of the square root of x squared plus y squared plus 1 plus 1. So in this case, if we actually compute this out, right, since 0, 0 is going to be part of the domain which is continuous, we have the square root of 1 plus 1, which is just 2. Okay, since the limit is continuous, or it's part of the domain, right? Because the domain for this equation right here, so if I were to have g of x comma y as square root of x squared plus y squared plus 1, my domain for g would be, so x comma y would be that x squared plus y squared plus 1 has to be greater than or equal to 0, right? That would be my domain. Right? And clearly 0 comma 0 is going to be greater than or equal to 0. And hence, this is going to be my limit. All right. So going back to that page, this could also lead to algebra tricks being used. All right. So example of this, as we just covered in this question, we'll be multiplying by its conjugates. Okay. All right, and that's number 17. Before we move on to 14.3, I want to go over one more question. All right, number 5, actually. So number 5, let's look at number 5. So, oh, okay, I don't know why I listed that down, but so I should go through it. This is one of, yeah. All right, so x squared y cubed. Okay, I think I know why. All right. So another thing I want to mention is that whenever you have a complete continuous solutions, just like this one, right? The domain works for all real numbers. that you can automatically say that the limit does exist, right? So from this, since you have a function, so fx comma y as completely continuous, I think that's what they call it, yeah, continuous, we can say that the limit does exist. Okay. And in this case, we can just prove it by just plugging in 3, 2. Now the limit as 3, 2, so if we plug in that, we get, what do we get? We get 9, yeah, 9 times 4 minus 4 times 4, and that's going to be 20. Okay. All right. Yeah, that's just another thing I want to point out is that whenever you have a function that's continuous, that limit does exist. So you don't have to go through all the different steps. Okay. And that's another way of tackling kind of the questions. We can just see whether a function is continuous or not, or yeah. So like if I were to look at the previous examples we've covered, we can see for number 17 that the parent function is a rational function, right? And if we plug in 0, 0, we clearly have a division of 0, and that doesn't work. Same thing with number 13, and same thing with number 11, right? And 9. So basically every question we've covered before. All right. All right, so if there are no other questions for 14.2, let's go straight to partial derivatives. So 14.3. So for partial derivatives, I'm actually going to go straight into questions or practice problems. Derivatives. Yeah, there you go. All right, so I have number 63 to 69. So let's see, number 63 to 69. Okay. Yeah, okay. So these are these are multiple partial derivatives. So yeah, I'm gonna skip through just finding first partial derivatives and just go straight to finding these indicated partial derivatives. Okay. So for 14.3, number 63, start off with that. Let's say we're given the function fx comma y is equal to x to the power 4, y squared minus x cubed, and y. And it tells us to find what fx is and find what f of x, y, x is. All right, so I'm going to start off with finding f of x. So f of x, so whenever you take, again, when you're taking partial derivatives, since I'm taking a partial derivative in respect to x, or another notation you can see this is possibly something like this, right? Something like this, right? Where you can use theta, or I just use basically a subscript of the function. So whenever you're deriving in terms like, let's say an x, we treat every other variable as a constant. So in this case right here, if I have f of x, deriving in terms of x, I'm basically treating y squared and y as constants. So in this case, I'll get 4y squared, x to the power 3 minus x cubed. Or, sorry, not x cubed, because again, y is a constant, so it would be 3y x squared. Okay, so that's f of x, or fx, right? Now, yeah, we can go on. F of x is, that's going to be deriving this in terms of x. That would be, again, 12y squared, x squared minus 6yx, right? And then lastly, taking the third partial derivative in terms of x, we get 24y squared x minus a 6y. Yeah, that's it. All right, so this is the third partial derivative in terms of x. And now let's try finding what f of xy is. All right, so we're solving, so that's number 1. It's number 1, number 2. Okay, so fxy is going to be the partial derivative of this, or this function right here, in terms of y, which is going to be 8y x cubed minus 3x squared. And then taking that derivative, or that partial derivative in terms of x, would give me 24y x squared minus, what is that, 6x. Okay. And that solution for number 2. All right, one interesting thing to note is that if I were to take fx(x) of y, right, and if I were to take fxy x, that should yield the same exact answer. Okay. And just to prove this, if I were to take fx(x)(y), that would be the same thing as what? 248yx minus 6. If I were to take this partial derivative, that would be 2048, sorry. Erase that. That would be 48yx minus 6. Right? So no matter what order you take the partial derivatives, as long as you take the same number of number of partial derivatives, you will yield the same answer. Okay, and that is called, that's a law in the textbook. Okay. All right, so that's number 63. 64. See if there are any other interesting ones. 64, goes on D, L, N. Oh, okay. Let me just go with one more in the respect of time. Yeah, we have 15 minutes, okay, because we still need 14.4. So let me just go over 68. 68 looks interesting. All right, so 68, we have V is equal to ln of r plus s squared plus t cubed, right? And we're trying to find the third partial derivative of V. It's back to r, s, and t. All right, so I'm going to start off by taking the first partial derivative. So I'm just going to do v of s first. V of s is going to give me 1 over r plus s squared plus t cubed multiplied by treating r and t cubes as constants. I get 2s right there. Okay, and then taking vs r, that's going to be, what's that going to be? So 2s is going to stay as is because it's a constant. I'm just going to rewrite this as, r plus s squared plus t cubed power of -1, and then 2s in front. So that'll be r plus s squared plus t cubed times to the power of -2 multiplied by a1, right? Because these two are constants, and then we still have a 2s in front. All right, so that's going to simplify to 2s over r plus s squared plus t cubed squared. Then lastly, we want to take the partial derivative in terms of t. Okay, so taking this in terms of t, we get 2s multiplied by r plus s squared plus t cubed power of -2 multiplied by 3t squared. That's going to result into 6st cubed all over r plus s squared plus t cubed squared. And this is going to be your answer. And just as I mentioned before, it doesn't matter what order you take. So you can take VR first, and then take VS next, or VRS, and then take the partial derivative in terms of t. So it doesn't matter what order you use, as long as you take the same number and type of partial derivative. Okay. All right, so I think if there are no other questions, I'm going to move on to 14.4. All right, perfect. So 14.4. Okay, this introduces us to the idea of tangent planes. All right, so we want tangent planes. So 14.4 is tangent planes. All right, so before we go into questions, I'm just gonna recall this equation, which is gonna be really important. So feel free, this should be covered in lecture Tuesday's lecture, I'm assuming. Yeah, this formula right here. Just gonna write it out first. Wait a minute. And plus fy of x naught comma y naught, y minus y naught. All right. So assuming we're given a surface f of x comma y, and we're given a point where you have x naught comma y naught comma z naught, right? The tangent plane of this surface right here is going to be this formula given right here. Okay, so we're basically gonna just utilize this equation that you guys have covered in lecture in order to do these kind of questions. All right, so let's see. So I have, 1 to 6 basically covers these kind of questions. And this should also be in the homework for this week. All right, so let's look at number 2. So 14.4, number 2. All right, so number 2 states that z is equal to x plus 2 squared minus 2y minus 1 squared, and then minus 5. And then tells us to find the tangent plane to the given surface at the specified point of 2, 3, 3. All right, so first thing you want to do is always take your derivative and find what f of x is. So like, find your partial derivative in terms of x and in terms of y. So in this case, my partial derivative in terms of x is going to be 2 times x plus 2. Since my y is treated as a constant and -5 is a constant. So that's f of x, and f of y is going to be the same thing as, what is that going to be? No, -4 times y minus 1. Yes, okay. All right, next thing you want to do is you want to compute fx at the specified point of, right, at x naught comma y naught, right? So given this point 2, 3, we get that fx at 2, 3 is going to be the same thing as 2 times 2 plus 2, which is the same thing as 2 times 4, which is 8. And then fy at 2, 3 is going to be the same thing as -4 times 3 minus 1, which is going to be -8. So if we compile the whole thing up using the tangent plane equation, I get z minus z naught, which is 3, which is equal to fx at x naught comma y naught, so 8 multiplied by x minus x naught, which is 2 plus -8 times y minus y naught, which is 3. Okay. So this equation right here is going to represent the equation of the tangent line. All right, so any questions so far? Now, another thing to note is sometimes they give, or they write this equation down as, where is it? So instead of z minus z naught, they also can replace this with f of x naught comma y naught. And remember, right, z is basically f of x comma y. And just based off this point right here, if 2 and 3 are my x and my y values respectively, my z value has to be 3, right? Or did I put x plus 2? Right, yeah. Right, so that would only mean that this point is in this surface right here. Okay, so this is just another way of saying of z naught as f x naught comma y naught. All right, let's go to the next question. So let's do number 3. Okay, so number 3. So actually, no, that's 1404. Sorry, let me just go back a bit. Yeah. Okay. Oh, okay. So let's go to number 3. All right. So number 3. So we have z is equal to e to the power of x minus y. And we have the point 2, 2, 1. Okay. This is probably going to be my last problem for today. All right. So 2, 2, 1, we have that f of x is the same thing as e power x minus y multiplied by 1, so that doesn't make a difference. And then fy should be the negative of that. There you go. Okay, because just using the chain rule, we get the derivative of y as negative 1. And then we have fx of x naught, y naught is equal to f(x) of 2, 2, which is the same thing as e to the power of 0, right? E to the power of 0, which is just 1. And then fy of 2, 2, which is going to be the same thing as negative 1. So we have that z minus 1 is the same thing as 1, x minus 2, plus negative 1, x minus 2. So if I simplify this out, I get z is equal to x minus 2 plus a negative x plus 2 plus 1. Oh, sorry, this is a y. Yeah, I was just figuring out where my y went. All right, so z is equal to x minus y. These two cancel out, and we have a plus 1 there. All right, so that's number 3. Yeah, we can squeeze one more in for tangent planes. Okay, so let's go number 6. Let's go number 6. Yeah, 6 is an ln function. So we have z is equal to ln of x minus 2y. And then we're looking at the tangent plane at point 3, 1, 0. So again, f of x is going to be the same thing as 1 over x minus 2y multiplied by 1. Now f of y is going to be the same thing as 1 over x minus 2y multiplied by negative 2, since x is my constant and y is the variable. And now fx of 3, 1 is the same thing as 1 over 3 minus 2. Right? 1 over 3 minus 2, which is equal to 1. And then fy should give me a negative 2. All right, and then now just compiling it, z minus 0 is equal to 1x minus, what's the point, 3 plus negative 2 y minus 1. All right, z is equal to x minus 3 minus a 2y plus a 2, which is equal to x minus 2y minus 1. So this is going to be my equation of the tangent line, or tangent plane, sorry. Okay, not a line, it's a plane. Yep. All right, hopefully that was helpful. Good luck with everything, and thanks for tuning in. I'll see you next week.